If you go to Thurstaston Common, SSSI, in summer, you'll meet about half a dozen Galloway cattle from Oldfield Farm, grazing the heathland. So this story starts when the National Trust and the then Nature Conservancy Council decided to reintroduce grazing to the common in 1982. And they wanted to monitor the effects, obviously, to see whether they got it right. Wirral Wildlife got involved about 10 years later. So this is the story of why in September each year, you can see a group of us heading on to Thurstaston Common with canes and tapes and a metal detector and a GPS and clipboards and a very regular volunteers. A number of them have spent over 6 years doing it, including all the people on that first, whose names are on that first slide. Rob will explain the background and then the analysis he's been able to do with the 39 years of data we'd collected by last year. We've just collected the 40th last week. He hasn't got that yet. Over to you, Rob.
Okay, thank you. I'll just put on the laser pointer. Okay, I should say that I haven't done any of the monitoring on this particular project. Can you hear me?
Yes.
Yeah. Okay, good, good. And there's some pictures of the cattle. And why are we interested in it? Well, I'm gonna talk about this because I was really quite excited about the process of how we handled this data and how we got a story out of it. But before we do that, I'm going to talk about what heathlands are, why we are, I am interested in them, why we should be concerned about them, and are we conserving them properly? Well, what are heathlands? Well, Charles Gimmingham wrote a book in 1972 which defined them as an open treeless tract that is dominated by low-growing evergreen shrubs that are mainly in the Ericaceae. Now, he's recanted on this definition a wee bit, but essentially they're treeless, they're low-growing, and they are dominated by the Ericaceae. But a bit that's not in the definition is the soils. They are on very, very, very infertile soils. On sandy soils like Thurstaston, where there's good drainage and the soil nutrients leach very quickly, and you get a pod soil. And here's a typical pod soil. You've got the acid, more humus, the leached horizon, and the deposited B horizon. Or you have organic soils where there's lots of nutrients, but the nutrients are locked up in the organic matter and they don't get through to the plants. Now, there's always an argument about heathlands or moorlands, moorlands or heathlands. I don't see much of a distinction, but generally speaking, it's based on elevation. So, Thurstaston. About 5 or 6 years ago, I did a web search, and of the 100 photos, only one actually showed a heathland. I was actually quite shocked. But anyway, it is an SSSI. It's an old common. It's 71 hectares. It's got podzolic soils, as I said earlier. And one of the things for designation is it's the largest and best remaining example of a lowland heathland in Merseyside. So it's got a lot going for it. And that's some of the species that you might find. Heather, Calluna vulgaris, obviously. You've got bilberry, wavy hair grass, which is now called Avenella, as opposed to Dischampsia. The gorse, Danthonia, and a few other typical heath species. In the drier areas, you would expect to have bell heather and western gorse, and the wetter areas, crossleaf heath, purple moorgrass, and so on. All of those things are found on Thurstaston. And there's some few birds as well. I have very little interest in birds, but I put those up for people who are more interested than me. Well, why are we interested in them? Well, my interest is purely theoretical, because they have consistently been a tool used to describe and test ecological theory. And developing techniques for manipulating them. And I'm sorry to say that all these days you do have to actually do some fairly advanced statistics. There will be none of that in this talk, or not much. But I'll go back to the dawn of ecology. It comes from Oikos, the house, and Logos, to study. And going back to the very start, you've got Sir Arthur Tansley, who was who more or less invented the term. He invented the term ecosystem, and he was one of the first British ecologists. He set up the British Ecological Society, the Journal of Ecology, etc. And one of his famous students, he had two really famous ones, was Sandy Watt. This is Sandy here. This is Tansley. This is that is Bernard Ford, and that is Captain Cyril Diver. And Sandy Watt really worked on Heathlands, and he inspired his great student Charles Gimmingham, who supervised Peter Bannister, and Peter Bannister supervised me. So I've always had a great interest in Heathlands. This is Charles Gimmingham here, and that's Peter Bannister here. But the person who started it off was Sandy Watt. He was a really great thinker, and he used Heathlands as a model system to describe pattern and process within plant communities. Change through space and time. He was really the first person that started to work this out. And basically, we all know this. If you start off with any bit of ground, you'll get some mosses coming in, some grasses, some shrubs, and some trees. This is typical ecological succession. And quite clearly, if you get some form of disturbance, you will get some form of replay back to the what was termed climax ecosystems. The point about Heathlands is there's something that stops that final succession to trees, and it's held in effectively it's called a plagioclimax or subclimax system. Now, one of what's great sort of pioneering bits of science was description of this cycle of heather growth. Pioneer to build that seedlings, to building phase, to mature, then it became degenerate, then it went back to pioneer. Now we've modified it since Watt's time, and essentially this is a management intensity gradient. Very low intensity, you'll end up with the degenerate phase, eventually going to woodland. If you've too much intensity, then you will end up with a grassland. The heathland, it's a Goldilocks state. It's somewhere in the middle where the management and the system has got to be just right. And quite clearly, the building phase can be burnt or cut, the mature phase ditto, the degenerate phase too, and that should drive it back to the pioneer phase. Now, what the National Trust is doing is they're implementing grazing and mowing in the hope that they can maintain this cycle. Now, that's what's called endogenous cycling. It's all to do with the life form of the plant that drives the system. But one of the things that happens is you can get large gaps caused by exogenous factors. Heather beetle is the obvious one, and that does occur at Thurstaston, but it can also occur through cold or drought. Perhaps not on the Wirral, but certainly in East Anglia, you would get this. And here, the heather is killed. That's the red lines. And in these large gaps, there's opportunities to go in different directions. You can get trees, seedlings coming in, going to woodland. You can get heather, which takes the cycle round again. Or you can get grass coming in, and particularly Avenella flexuosa and Millennia caerulea are the two grasses which often take over and dominate. So essentially, what we're trying to do in heathland management is to maintain this cycle through some form of management and not allowing it to go to woodland and not allowing it to go to grassland. That's the aims. So we're not sure how much heathland was around pre-human. There must have been some, but most heathlands these days were formed by man. They're created and maintained by human activity, cutting, burning and grazing, and those activities were part and parcel of, I guess, peasant society actually maintaining its ability to survive. But whatever happens, it seems sensible to maintain them using similar management. And if that's the case, you need to monitor whether the management is working or not. And that's the point of the study at Thurstaston. Now, at this point, I'm going to move on to the monitoring scheme. And I wasn't there at the start, but it was actually started by Philip Rothwell, who set up some quadrats, and Andrew took them on. So I'm going to call him the pioneer, the person that sort of really got the system going, although it was based on some of Philip Rothwell's quadrats. And then you need a Hilary. And this is very, very important. Now, I've known Hilary since 1978, when she joined Tony Bradshaw's group at Liverpool, where I was a postdoc at the time. And you need somebody like this, somebody who, to put it bluntly, is bloody-minded, keeps going, pig-headed, you might say, somebody who really just keeps doing it. And you need to have that in a long-term system. You need to have somebody who is a bit on the dogmatic side, but just keeps going. That's very, very important. And she's so important, she's even got a computer sign named after her. Now, one of the things about people who run long-term monitoring schemes is they can sometimes get very defensive. And luckily, Hilary is not like that. She's got lots of volunteers who've helped in the field and data curation. Because in every long-term scheme, you must have some form of succession plan. You must have one. And luckily, there's enough people around who know what to do. And lastly, you need a geek who can analyze the data, and that was my job. So the monitoring scheme, it's only 12 quadrats. Normally, that would not be enough for any sensible piece of scientific work. They're rather large. They're 5 by 5. That's bigger than most, and certainly bigger than the NVC recommends for heathlands. They measure the visual cover of all vascular plants, plus 2 Bryophyte groups, the heights of some species, a letter-coded vigor score, and this is done in September. And as Hilary has just corrected me, it started in 1982 and is now gone on to 2021, so it's now 40 years. Unfortunately, we've only got 39 here. So that's basically it. I'm very chuffed with this, because this is the first thing I ever produced in GIS. So it may not be great by GIS aficionado standards, but to me, it's pretty good. You can see the 12 quadrats around the place. There's 3 paddocks, and that's the outline of the SSSI. And I've got a Gantt chart. This is really when things started. These were the initial quadrats. They were expanded in 84 to 86, expanded again in up to 89, and then there was some sampling between 1991 and thereafter. All 12 have been measured every year, except that one, because Hilary was ill. That was very naughty, so kindly see it doesn't happen again. And I'd call it a demonic intrusion, and anybody wants to read that paper, it's absolutely brilliant. It's actually quite funny, but certainly it's important to realise that things out with your ability to do anything about sometimes interferes with long-term research. COVID last year was one. Anyway, I sometimes go to the World Wildlife Monthly talks, and we got on talking, and I've got some long-term data that needs something doing with it, and I very stupidly said, I suppose I could give you a bit of a hand to do it. Well, I forgot all about it, of course, but Hilary remembered. And then she admitted a few weeks ago, I've been looking for somebody to do this for years, and I haven't got mug written on my forehead, but perhaps I ought to have. It was quite fun, really. Anyway, but when I got the data, and this is from now on, the next part of the talk is actually looking at different types of thinking and how to make it easier to analyze data, because it's actually very important. There's no point in collecting data unless you're going to analyze it. Now, Hilary, you inherited a field record sheet, which is perfectly acceptable. It's absolutely fine. It's got ease of use, it's common sense, in the field it's great, and Hilary had done the decent thing and put half the data into an Excel spreadsheet with each page for each year in a separate page. Now, unfortunately, to analyze this statistically, this is just not on. You really do need to completely restructure the data. And for a start, here you've got quadrats along the top. That's absolutely not possible. You need to have the species along the top. So the whole thing needs to be transposed. But essentially, it is it needed an awful lot of reworking. So the next few slides are about how we reworked it. But I should actually start by saying that's not the way I would do it. I would start off with an experimental design and the statistical analysis. And once I got that right, and sometimes my colleague and I would argue for 6 months before we got to this point. And then we put in the data collection sheet, the spreadsheet, and then the statistical analysis. And quite clearly, the statistical program informs how you do the data collection and the data input. So we needed to transfer the existing Excel data into a new format and type in all the older data and transfer this into the new format. And I can say this was non-trivial. It was a substantive job. And what we did was we created 4 worksheets. The first one is a species dictionary with species names and 2 to 3 letter abbreviated codes. Now, why 2 to 3 letter? Well, it's actually because species names are quite long, and you can use them in analysis. You can use them as variables. It's not a problem. You can do that. But when you plot them, because they're so long, they run over each other. So we did that with a 2 or 3 letter abbreviated code. Worksheet 2, this is the big data set, really. This is the most important one. The cover data, that's all the vascular plants and the other groups. Workshop 3 was the height data, so we separated cover from height, and we also separated the vigor scores. And separating these is really important because they are all different. They're just different, so separate them out. So that's the first job we did. And as I said earlier, the column headings have got to be the species. So here they are: Clera vulgaris, Erica cinerea, Erica tetralix, etc., etc. And they have to be there. They just have to be. We had 460 rows of data, 12 by 39. We didn't have any black cells. We put an NA, that's the missing value indicator that I use. And one of the other things we do, and I found this very useful, is column A is just an index. And that's very useful if you want to sort and resort data. You can always get back to where you started if you've got an index column. B is the year, that's the quadrant number, that's the year of sampling, and we created an elapsed time. And one of the reasons we created an elapsed time is graphs find that I get very messy if you use big numbers. So elapsed time is much smaller, and we set that with 1980 is year 0. So effectively 1980 minus 1980 is 0. So that and the species codes are basically to make it easier to plot graphs. And of course, these columns here, B, C, and D, allow us to uniquely attribute every row of data. So that's 1, 82, 0. There is no other row in the data set that has those 3 codes. So we can now look at this, how long it took. It took us a year, not full time, a load of volunteers, Hilary and myself. It was a big job to get the data in good order and to double and triple check it. Each year, we've just got 220. We just add it onto the bottom of the spreadsheet. It's a simple cut and paste job each year. And in this form, the data can be read easily into most statistical packages. I used R because it's free and it's also very good, but other ones that would do the same. And there are errors. There will be errors. It's absolutely inevitable there will be errors. There is no data set or any substantive data set that doesn't have errors in it. And I reckon there's probably less than 0.04% because I've done a bit of checking. And all of those need careful checking and correction. There'll still be errors, but they are very, very low. And here are some of the errors that we found. Uppercase 0 instead of uppercase O instead of 0. L, lowercase l instead of 1. Inclusion of non-numeric symbols, and this is where you're taking notes, you write something in, and we had the tilde, we had the slash, and we had dashes. Sometimes that indicated two measures were made in the same quadrant, so I took the average. Sometimes if you get this little dash in, the data automatically in Excel comes to a date. I have no idea why this happens, but it certainly does. And all of those were double checked and replaced. And sometimes people are very keen and put units into the Excel spreadsheet. They are really best kept outside within a meta-analysis sheet, and you should only ever have numbers in a number sheet. Now, I'm sorry if this is preaching to the converted here, and you know about this, but really these are the sorts of things that we picked up. It didn't take long to sort, but we did actually have to do this. What I found actually for putting data in is if you use voice recognition software and use the numbers only option and just speak the numbers in, it's much, much more accurate and much easier to do, in my opinion. Only then can you actually start on the analysis. Well, you can do it all in Excel. Here's an example. This is a perfectly acceptable Excel graph, and you know, it's okay. You could put all 12 quadrats. This is just one quadrant. You could put all 12 quadrats on here, and it would be a colored mess. It would be very difficult to interpret. You could also do each graph individually. I chose not to do that. Oh, these are some of the difficulties. If you do different graphs, you might have differences in scaling of the y-axis. Fitting statistical trend lines is much harder in Excel, and it's very limited. And basically, other programs allow you to do it much more efficiently. This is one graph. We've got 49 variables times 12 quadrats to do. That's an awful lot of individual graphs. I have actually plotted all the graphs out because that's what people want to see. Well, I've done it using an R script, and this is all 12 quadrats plotted in the one graph showing the changes in header over time. And you can see that in quadrant 1, there's a very clear reduction. I should say these statistically fitted lines are rather for show rather than substance, but they do help to show you some of the trends that are there, but they don't take any notice of the actual statistical values because they're just a smooth fit. But you can see that quadrant 1 header is going down. In 2, it dropped very early on. It recovered a bit, but it's going back down again. The same sort of thing in 3. It's flattened off a bit. It's going up in 4, possibly going up a wee bit in 5, fluctuating a lot in 6, coming down in 7 with fluctuations, a bit of a boost in the early stages, then a reduction, and so on and so on. So we've actually got a very clear, if you like, description of all the quadrats in one graph very, very succinctly. And to get another species, you just change the CV code to something else, like UG, for Ulix gallii. And here, I mean, I've only plotted 6 of the plots where Ulix gallii are present, and you can see that here it's gone up. So we've got a reduction in Kaluna, but you've got an upsurge in Ulix gallii. In 2, it's pretty well stable. In 3, it's fluctuated a bit, still a pretty low. 4, not very much, and it's increasing in both 6 and 8. So we've now got a graphical representation of every single species within the data set. Here's some more. These are for the wetland plots. You can see that this is 4, 5, and 10. You can see that Erica tetralix has increased, but now it's dry. It's gone down again. It's gone down consistently in 5, and although it's peaked early on, it's actually reduced, although there's a wee bit of evidence that it might be increasing again. Millennia, a reduction, although it's stabilized. And this plot is going up, but now coming back down. And in 10, it's reducing almost to 0. Drosera rotundifolia, it's not good news. It's actually almost disappeared from the 2 sites in which it was present. And the bog mosses have shown fluctuations. So we've got a very rapid way of looking at all species with respect to change through time. Here's the tree height, and you can see that the tree height is actually pretty good in most of the plots, but some of them there's been quite a considerable increase. It's come back down again. It's increasing a bit there. And this plot here, it's all over the show. And obviously there's been some form of cutting going on in that area there. So given that we know what's going on in the plots, we can start to interpret these data in a kind of sensible manner. Now, this is where I really enjoy describing how data can show pattern. And this is a statistical method that uses all the species data at once. Now, a lot of people think it's complex, but the outputs are very, very simple to follow. The aim is to produce a graph that you can infer gradients from the data. So this is my simple explanation. I apologize if it insults people who know more about it than probably I do. The data collected, all of it, all the species cover data rather, for all 12 quadrats for each year. And it's like going through a mathematical food blender. And I don't know what it does in there. It just does it. It turns the stuff up and then it puts it through what I would call a mathematical sieve. So it keeps the best bits, the stuff that tells the story. And when you make a graph, you get some form of gradient. And here I've got the carrots going up in size and the beans going down in size. But essentially you are using mathematics to produce a series of gradients. And importantly, in the same analysis, you got an assessment of the species, an assessment of the quadrats. And essentially, species that are close together are responding together, quadrats that are close together are similar, species that are far apart are different, and quadrats that are far apart are different. It's as simple as that. And here is and this is actually what we did, if you're interested. We used detrended correspondence analysis, DCA. We transformed the data to Hellinger. We removed species that were only present once because they just get in the way. And then we correlate it with elapsed time. And then we put some standard deviational ellipses on, which show where the quadrats were in the graphical space. Now that sounds complicated, but actually that's the graph that's produced. You've got the 2 gradients, dry to wet, wet to dry. And you can infer that because here you've got Erica cinerea, Ulix gallii. Kaluna vulgaris is in the middle. And at this end, you've got things like Trichophorum, Millennia caerulea, Erica tetralix, and Drosera. So it's quite obvious that that is a dry-wet gradient. This one's a wee bit more complicated, but it's a sort of open heath woodland gradient. Here we've got Dryopteris dilatata, you've got oak, you've got Anthoxanthum odoratum, Galium saxatile, and Rubus fruticosus. And up here, you've got Sartica dioica, Festuca ovina, and the more heathland species. So we've got a sort of gradient, and we can plot. Now, I'm only going to do this for what we term the dry heath quadrats. This is the share of the space they take up, and you can see that all of them, all of the dry heath quadrats, have got some space below this line dipping into the area that's got a woodland tendency, and one is very, very large. It certainly has had woodland type species in it, at least at some point during the period. If we look at the trajectories, it starts there and it goes right the way down to here, then it comes back up again. So that's had a massive shift towards the bottom end, the more woodlandy end of the communities, and then it's come back again. So that's actually good news. All of the other dry heath quadrats have moved in this direction a bit, but at least they are moving back towards where they should be. And we created a traffic light system based on movement from start to finish. Where's the start point? Where's the end point? And you can see that these ones here have moved very little, these ones have moved a bit, and these ones have moved the most. So we'd expect that these ones might be the ones where there's the biggest problems. However, we've actually managed to separate them into the three groups. The traffic light system separates them into different classes, but there are some problems with this. I mean, I set these thresholds rather arbitrarily. It just so happened that the points were 1.5 and 0.5 and they fitted, so I used them. But the real issue is the baseline. And in any heathland, or indeed any ecological analysis, the baseline sets the standard. And in this case, the baseline might not have been particularly good heathland. It may have been, but you know, we're moving away from a baseline, irrespective. And you know, it may well be that that was not the best place to set our starting point, but that's where we are. And it's important that 3 of the 4 red light communities are in the ungrazed area. And that really emphasizes the importance of management. I should also point out, if you look at this baseline approach, if you look at most indicators of environmental change, they're usually set to a baseline in 1970. That was European Environment Year, the first European Environment Year, I believe. And that's fine. So change it from that year is where we are. But you know, 1970 was chosen because it was 1970, and you know, it may be that that's not the best year to use. And to the conclusions that we've got our quadrats separated into 3 moisture groups: dry, intermediate, and wet. Some of the dry and intermediate heaths are showing unfavourable successional movement, but most show some sign of recovery, and part of that is due to management. Wet heaths appear to be getting drier, and that is actually quite potentially worrying. And we've highlighted dry heaths as the area of immediate management concern. And there, I'm going to finish off with a nice picture of someone saying hello to a cow. And you can see that here we've got a rather nice heathland. You've got some problem species. You've got birch coming in here, though. You've got some bracken encroaching. But apart from that, it's a rather nice, probably building stage going on to mature stage heather. And quite clearly, the data that we get from the monitoring system is given to the National Trust, and Hilary is going to talk about that. Over to you, Hilary.
Just very briefly. So yes, National Trust get this data every year, plus whatever notes we make in the field at the time, like this compartment's getting an awful lot of birch and needs something doing about it. And this does guide the management, but it also justifies it, because Thurstaston Common has got no direct form of income from its visitors. There's no charged car park or anything like that. And management costs money, even when half a dozen cows do some of it for you. So it justifies to the higher ups of National Trust as to why this management's worth continuing and putting a bit of money into, mostly in scrub clearance. When we look at some of those graphs that Rob has shown in detail, well, we could pick up, oh yes, that's the year that quadrat 7 was mown. So the heather went right down, but it's coming up again, and coming up again as lovely pioneer heather, not a degenerate heather. Earlier on, we can pick up one that had a controlled burn. And we can also see on the wetter quadrats, what should be the wetter quadrats, the rise in heather, which shows it's drying out, which is bad news. This is one of the wetter ones. You won't be surprised to know from the standing water in that corner. It isn't usually as wet as that, but it was that day. So the data helps to justify to National Trust the continuing management to keep the heath in relatively good condition. And what Rob was saying about baseline, in fact, that 1982 baseline was mostly not high quality heath. That is why National Trust wanted to bring the grazing in, along with the Nature Conservancy Council at that time, to try and improve the quality of the heath. So we're not actually starting from it being in perhaps the condition it was in 1920. When National Trust start buying areas of it. Anything else I was going to say? The Drosera, the sundew, has indeed actually completely died out as far as we know. Nobody's seen it anywhere on the heathland for a good decade now. So that's a lost species that has gone with the drying out of the wet areas and possibly increasing shading in between attacks on the trees. So that's, and perhaps the only other thing to say is that Oldfield Farm do sell their beef over the internet if you're a meat eater and like to have some relatively sustainable beef to eat.